Hello everyone, I am Abhinav and today we will be discussing the very first problem from the CP-31 sheet by TLE Eliminators under the 1500 rated questions. Okay, so let's begin. We'll move to the CP-31 sheet and there we can see that the 1500 rating mark has been checked. We can find the clickable links to our problems. Okay, so let's click the first problem, which is greetings. So fine. Okay, let's read the problem statement. There are n people on the number line. The ith person is at point AI and wants to go to point BI. For each person, AI is less than BI, and the starting and ending points of all people are distinct. Basically, we are given that there are n people. They are on the number line, and for every person, we are given their starting point in the form of AI, and their ending point is BI. Okay, so we are giving the starting and ending points on the number line of n people, and those two n points, the n starting points and the n ending points, they all are distinct. This is also given to us. Okay, now we'll see that all the people will start moving simultaneously at a speed of 1 unit per second until they reach their final point BI. When two people meet at the same point, they will greet each other once. How many greetings will be there? Okay, so now we are given that they all would move at a speed of 1 unit per second. Okay, so all of them would start at their starting point and they would together move at a speed of 1 unit per second until they reach their final point BI. They would keep moving. After that, they would stop there. And whenever two people meet each other, whenever they cross each other, or when two people are at the same point, they would greet each other. And we need to find the number of greetings that would be there in total. Okay, and the clarification is given that a person can still greet other people even if they have reached their final point. Okay, so whenever a person reaches this final point, he would stay there, and whoever crosses him, he would greet him. Okay, we need to find the number of greetings. So I hope the statements are clear. Okay, let's see the first example to understand more clearly what we need to do here. Okay, so you can see in the first example, we are given that n is 2. Basically, n is 2, it means there are two people on the number line. For the first person, he is starting at point 2, ending at point 3. For the second person, he is starting at point 1, ending at point 4. That's what we are given. Okay, so we can look at this on a number line. Okay, let's say the first person is starting at some point 2, he is ending at some point 3. Now the second person, he is starting at a point 1, ending at a point 4. Okay, these are the starting and ending points. So for this test case, what would be the case? It means at t equal to 0, we can say initially the first person would be at point 2, there his initial point. The second person would be at point 1, his initial point. So initially this is our condition. Now what would happen after 1 second? Okay, after that they would start moving at the speed of 1 unit per second. Both of them would move together. So after 1 second, the first person, he would reach point 3, the second person, he would reach point 2. Okay, so in the next second, the first person would be at point 3, the second person would be at point 2. Okay, now after this, since 3 is the ending point of the first person, he has already reached his final destination. He would not move further, he would stay there. But since this first person, he has to reach till 4, so he would keep moving now. So in the next second, what would happen? He would stay here. So the first person would remain at point 3, and now the second person has moved from here to, and he has also reached this point 3. So at point 3, both of the person would meet each other, and there we would have one greeting. So we can add plus 1 to our answer. We would have one greeting here when both of them would meet each other at after 2 seconds basically. Now after that, what would happen? Since 3 is at his the first person is at his final position, he would remain there, and this second person, he has to reach up till 4, so he would keep moving, and after this he would have reached his final position also, which is point 4. Now both of them are at their final position, nobody would move further, so there are no more greetings. My final answer would be 1. There was only one greeting here when both of them crossed each other. Okay, so for this test case, my answer would be 1. You can verify that for the first test case my answer was 1. Okay, now what if there was one more person? Let's say instead of 2 we had 3 people, and there was one more person, 0, 6. Let's say he starts at some point 0 and ends at some point 6. Okay, so now what would happen? Okay, let's see what would happen in this case. So again, same thing. Initially, the first person is here, second is here, third is here. So they would stay at their initial positions, which is 2, 1, and 0. Okay, this is where they all would start from. After that, they all would start moving at a speed of 1 unit per second. So he would have reached here, the second person would have reached here, the third person would have reached here. Okay, after the next second, since the first person has already reached his final destination, he would remain here, the second person would move here, and they both would be at this same point in the next second. And so we can say initially there were 0 greetings. We can say we can add a +1 to our answer, that yes, they would greet each other. And for the third person, he would, from here he would move here. Okay, so this would be the position after 2 seconds. Okay, now at t equal to 3 in the next second, what would happen? This first person has already reached his final positions, but this second person, he would move further, the third person would move further. So the second person would now be at his final position. First was already there, and the third person would move here and he would greet the first person. Okay, so this person would have moved here. So now both of the first person who is at his final position and the third person, they would greet each other. So we can say that we can add a +1 to our answer here. Okay, after that, what would happen? He has reached his final position, he has reached his final position, they would not move further, they would remain at their final positions. And the third person would move from here, he would move further and reach here. So he would basically he would greet the next person, the third and the second person, they would greet each other. We can add +1 to our answer. After that, the next second, this third person would also reach, he would reach 5. Okay, there's a 5. After that, there's a 6. Okay, he is at 6 and there's a 5 also, which we can just denote. That's not the ending point of any person. So next second, what would happen? This third person, he would reach at point 5. The first person would be at his final position, second person at his final position. There are no greetings here. After the next second, the third person would also reach his final position here. So all of them have reached their final positions, no more greetings here. So now this process will stop. How many greetings did we get? We got in total 3 greetings. So for this test case, for the modified version, our answer would be 3. Okay, I hope you understood the problem, what we have to do. Okay, so with this diagram, now let's see how can we solve this problem. Basically, how can we find this count, the number of greetings? Okay, so let's look at the constraints of the problem first, so that we can know what all solutions would be acceptable. So we can see that n is up to 2 into 10 to the power 5, and the ai and bi, these are minus 10 to the power 9 to 10 to the power 9. So overall, the sum of n doesn't exceed 2 into 10 to the power 5. Okay, so we can say that n is less than equal to 2 into 10 to the power 5. This is our constant, and these points, they are ai and bi. They are in the range from minus 10 to the power 9 to 10 to the power 9. So one way was, whatever we were doing, if you do the brute thing for all points one by one, 1 second, if you just keep moving, then the points are in the range of this. So you would have to move something to into 10 to the power 9. These many points can lie in your number line. If you are doing one by one, then doing this much brute is not sufficient, you can obviously understand. So we need to utilize this thing. Basically, we need to find our answer in just by using the endpoints. So what complexities, in what complexities can we solve our problem? Let's say we are solving our problem in O of n square. If we are using an n square complexity total, that would take 4 into 10 to the power 10 operations, which is much greater than 10 to the power 8 operations that we can do in 1 second. So we can say we cannot have a complexity of O of n square. We need to have it something more optimized. So basically, what acceptable complexities would be there? We can say we can write a solution in O of n log n or O of n, something in this range. We need to write our solution in somewhat in this range. This we can understand by looking at the constraint of n. Okay, so this we can say is our expected time complexity. Okay, now let's see how can we solve the problem in somewhat in this time complexity. Okay, so like before solving, so for solving only, let's look at some observations that we can get. So while doing this dry run only, you would have got a few observations. When does a greeting occur? Okay, let's analyze when would two people greet each other. Okay, let's say this first person and this second person. Let's look at them. This first person was at point 2 to start with, the second person was at point 1 to start with. So the first person was here, second was to the left of him. So once a person is to the left of someone, if both of them are moving at the same speed, he would remain to the left. He can never cross him until one of them stops or slows down. Okay, so since both of them are moving at the same speed initially, he cannot cross him. So there can't be a greeting until both of them are moving at the same speed. When would there be a greeting? Is when this person stops here. Okay, so they are moving. Okay, now what happened? This person has stopped here. Once the right person has reached his final destination and the left person is still moving. Okay, if the left person is still moving ahead of him and if he crosses him, then there would be a greeting when he crosses him. So basically we can say a crossing can only happen when the person to the left finishes to the right. Okay, so this was the route for the first person. If the second person who is starting to the left finishes to the right of him, then we can say there would be a greeting. What if the first person finishes here only, here somewhere only, this first person is finishing. Let's say this is 2.5 instead of 4. Then what would happen? That they would start here, this person has reached here, this person would be somewhere here. After that he has stopped here and he would also come and stop here, he would never cross him. So if it's the case of something like this and like this, these two ranges, then they would not meet each other. When would they meet each other? Is when there is something, this person, the range for starting and ending point for the first person is this, and the second person is basically covering this range. He is starting before him, ending after him, then only he would cross him. Okay, so the first conclusion that we can draw from it is for two people to meet, if two people are on a number line, then if I am telling the first person is I and the second person is J, then AI is the starting point of the first person, BI is the ending point of first person, and let's say AJ is the starting point of the second person, and we are saying this AJ is less than AI. Basically the second person is starting to the left of the first person, then until they both are moving together he can never cross him. Okay, he would remain behind. Now once he has reached his final destination, now this guy would be somewhere behind him. He would cross him only if his ending point is after BI. So we can say he would cross him if this BJ is after BI. So our condition is basically that if AJ is less than AI, then it implies BJ should be greater than BI. Okay, so we can say if both of these conditions are satisfied for 2 points to meet each other, then basically these two people to meet each other, then we can say that these two people would meet each other if this condition is satisfied. This would be our condition that should be satisfied. Okay, so now we know this condition. Now how can we solve this problem? Okay, so what a brute approach that would come to your mind is basically check this condition for all pairs of people. Okay, at max how many greetings can be there? At max any two people would greet each other once. Okay, so for every pair of people, okay, there are n people. Okay, how many pairs would exist? So it would be nc2, or we can say n into n minus 1 by 2. These many pair of people exist. Okay, so for every person check him with all other people. Okay, for this person check him with all the other people, for the second person check with all the other people. So if you are doing the brute force approach of checking every person with every other person, this thing is taking a overall complexity of O of n square. You are running in something order of n square times, and then this checking condition is a constant time operation. If this condition is satisfied, do a plus 1 to our answer. So with this approach you can solve the problem in O of n square, but as we know this time complexity is not acceptable, we need to optimize it. Okay, now how can we find some better approach? So now what can we do is the thing. So now to find something better approach, let's try to find some patterns. How can we basically analyze this problem? So instead of looking at the problem as people who are traveling, we know the condition for two people to greet are just based on their ranges. If we know the starting and ending point of the first person and the starting and ending point of the next person, and if we can denote the starting and ending point as some range, we can say that this first person is in this range, this starting and this ending point, second person is in this range. So if one of the range is entirely covering the other range, okay, so for this person this second range is entirely covering him, then we can say that the two people would meet. And if for this person a range which is not covering, crossing something, for that won't be counted to our answer. Okay, so basically we can reduce the problem to that we are given, basically in a number line we are given, let's say, n ranges. Okay, n ranges of the form ai to bi. Okay, so we are given n ranges in the form of ai to bi. So let's say this is one of the range. Okay, let's say this is one of the range. I am taking some random ranges. Okay, let's say this is other range. Okay, these are basically the AI and BI that we are giving the starting and ending point of the people. We are considering them as some ranges. Okay, let's say this is some other range. Okay, so we have like one, two, three, four ranges. Okay, if let's suppose these four ranges are given to us. Now, how can we solve this problem? What we can say is, uh, what approach can you think is basically first, in order to analyze them, let's look at them in some order. So let's sort them up. That's the first thing that would come. Sorting is something, whenever you need to do some greedy things, sorting comes first to your mind. So either we can sort them on the basis of their starting points. Okay, these ranges are given in some random order. Maybe this is first, this is second, this is third, this is fourth, any order. So first let's sort them. Let's sort them on the basis of their starting point. Okay, we can also sort them on the basis of their ending points. Okay, just do any one thing. Let's say I'm sorting them on the basis of their starting points. Okay, so I would say that this range is the would be my first range in my sorted order. This would be the second, this is starting next, this is starting next, this would be third, and this would be the fourth. Now we have sorted our ranges. First this range, then this range, then this range, then this range. Now in the sorted order, how can we analyze a range? So what was the count that we needed to find? That were the number of pairs that satisfies this condition, that one pair uh, completely overlaps the other pair. Okay, so for every pair, so for every range, basically for every range, we can say how many ranges overlaps it. Add that to your answer. Okay, so for this third range, if we are analyzing the third range, we'll say this second range completely overlaps it, this first range completely overlaps it. So for this third range, add a +2 to your answer. Okay, same thing do for every range. So we'll start with the first range. How many ranges are completely overlapping it? There is no range that is completely overlapping. So for first, we would add a +0 to our answer. How many ranges are overlapping this second range completely? This first range is completely outside this second range. Okay, completely covers this second range. So for the second range, there is one range, which is the first, which is completely covering it up. Now for the third, how many are there? For the third, we can say this second as well as this first, they both are covering him up. This fourth is not covering because it's starting from inside, ending from outside. Okay, it's crossing. So these 1 and 2 are the only two ranges that is covering this 3. So for 3, we'll add a +2 to our answer. Now for 4, how many ranges are completely covering it? It's only the first range. Okay, because for 4, this second range is crossing, this third range is also crossing, but this first range is completely covering it. So for 4, we can say we'll add a +1 to our answer. So add these values up, in total we got 4. So for this particular case, we would say our final answer is 4. Okay, so that's how we are calculating. Now how can we do this efficiently? That's the question. Okay, like one way was that brute approach, which was taking off n square. Now to do this also, for any particular range, if you are checking for all the ranges how many are completely covering it, it would again take O of n square time. Now you need to optimize this thing. For a particular range, how can you count how many ranges are covering it in some, maybe some less than O of n time? That's your problem. So what we did, we have already sorted the ranges. Okay, so when we are moving in a sorted order, we know if we are at some range, let's say ith range, okay, we are at this range, then we have already the first three ranges are already analyzed. We are considering these ranges are already analyzed when we are at the fourth range. So all those ranges which we have already seen, which are already analyzed, they would be starting before this. Okay, now all these ranges that have not been analyzed, they are starting to the right of this, so we don't need to consider this. What we need to find, that for this range, all those ranges that would be covering it would be starting before it and ending after it. That's the condition. So the starting before condition is already done if we are moving in a sorted order. All those ranges that we have seen, they are the only ones that are starting before it. Now among them we need to find how many are ending after. So among these three ranges, these two were ending before it, but this one range was ending after it. So for 4 we had this plus 1. Okay, so for every ith range, what we need to do is all those ranges that have occurred before, among them how many are ending after this. This is what we need to find. Now how can we do this optimally? So like if we are storing these ranges in some data structure, let's say while moving in this sorted order, all the ranges that we get, we are storing them in some data structure. Okay, now from that data structure we need to find how many have ending values greater than some value x, the ending point of this range. So what's the best way to do this? Let's say you are using a vector to store them. So if you are using a vector to store them, then in order to count how many in that vector, the ending points are in some random order, because it's not necessary if starting points are sorted, ending points would be sorted. They would be in some other order. So in that, to find how many are just greater than this, you would have to do a linear search, and that would take O of n time. Now what if you have stored the ending points in some sorted order? Then you can do a binary search and find how many are just greater than this. But if you are storing the values in sorted order in a vector, then while inserting, to insert in a sorted position, the so if you are using a vector, okay, there are two options. Let's say you are using just a vector in any order, then insertion would take O of 1 time, but the checking thing, the counting thing would take O of n time. But if you are using a vector in sorted order, then the checking, the counting thing could be done in O of log n time using binary search, but the insertion in a sorted order would again take you O of n time. So overall we have to do insertion as well as checking, both of the things. So it would again take O of n square time in total. You are doing this n times. So what other thing, we also have a set if we need to store things in sorted order. Let's say we are using a set, then insertion in a set would take log n time. Okay, that's fine. But in a set, checking how many values are greater than a particular value, for a normal set you cannot do. Through a binary search you can find the value just above it, but you cannot count how many values are there, because in a set there is no indexing. Okay, so in this thing would take again O of n time. You would basically count one by one, just go to every element and count. So in order to do both of the things in log n time, what we use is something called a ordered set. Okay, it is a set only, but a special type of set, which is called ordered set. Okay, which is not contained, like, if you don't know about ordered set, I'll tell you briefly what that is. But this is a very useful data structure which you should know. Okay, so if you are solving this problem, I would recommend go and learn more about it. I'll tell you in shortly what this thing is. This is basically a set only with two extra functionalities. Now this is not present in your STL library, but this is present in PBDS, which is policy based data structure. This library, you have to include this library to get the functionality of an order set. In the code we'll look how we include this library and use this set. Okay, This I am telling for C++. You need to include this library and use it. I'll show you the code. Now, if you what does this order set mean? It's same as a normal set. All the functionality of a normal set are present here. All the insert function, the upper bound, lower bound functions, all of them are present, same as a set. Along with that, there are two extra functionality to it. One is, if let's say I'm declaring an ordered set, the name of the set is st. Then if we write st dot order of key, we can write st dot order of key. Here we can pass some value, let's say x. Now what this function would return me, this function would return me this. First of all, it would work in log n time. Okay, this function would work in log n time, and it log of size of the set, n is size of the set. In log of size of the set time, it would return me how many values are strictly greater than x or strictly less than x. Okay, this is what it would return me. So this would just return me basically the position that x would be placed in the set if it is inserted in the set. So basically the order of key, what would be the order of this key x. So how many values are less than x in the set, that would be returned by this function. Okay, now the second functionality that it gives me is st dot find by order. Okay, x. So it would return an iterator, so we need to use a star to get the value. This again in O of log n time, it would return me the basically the index, the value at index x. It will do the opposite thing, that what's the, if the set is arranged in a sorted order, what's the value at the xth index. Okay, that it would return. It would return an iterator to that. If you do a star, then it would give you the value. So these two extra functionality that can be done in log n time is provided by this ordered set, and using this ordered set you can easily solve this problem. Once you have inserted it in log n time, you can do the checking thing in O of log n time. So using an ordered set, I am writing it at O set, you can do the insertion in O of log n time and the checking also in O of log n time. Okay, what you need to check is how many values. So among these, if they are inserted in your set, so we would insert the ending points of these, not the starting points. So we need to check for ending points. So among those ending points, how many points are greater than something. So if we can find using this function how many are less than x, then we can just subtract from the size of the set. If we can from the size of the set, if we subtract this value, how many are less, we'll get how many are greater than x. I think that is clear to you. So this way we can find how many values are greater than x, and that we can add to our answer. That way we can do the whole thing. These two are done in log n time, that is done n times. So the whole operation would be done in the overall time complexity of O of n log n using an ordered set. I hope you got. Let's see a quick dry run to understand what we are doing here. Okay, so let's take a test case. Let's suppose we take this second test case. Okay, so what we would do here is, first of all, we would sort this array based on the starting points. Okay, so if you sort them in starting points, 2, 100 would come first. After that, I think -2, 100, and then 1, 8, then 2, 6, and then 3, 9, 4, 5, 7, 10. I guess this would be our array sorted based on the starting points. Okay, now once we have sorted this, what we would do is, one by one we would move in this sorted order, and we would insert these ending points into our set. Okay, and while inserting, before let's say we have inserted these three values. Now when we move to 9, what we would do, we would check how many values in the set are greater than 9. So the number of values that are greater than 9, those would be the we would add that much to our answer. So that way we can just basically traverse uh, this whole array in sorted order, and then we can compute our answer. Okay, so let's say we would start from here. Let's say we have our set which is initially empty. Okay, so first our I would be here. Okay, this would be the first element. Now first we would check how many values in the set are greater than 100. Now since the set is empty, there are no values which are greater than 100, so we add a +0 to our answer. Okay, and then we would insert this 100 into our set. Okay, so this 100 has got inserted into our set. Now we would move to the next value. My I would move here. Okay, now what we would do, we would check how many values are greater than 8. So how many values are greater than 8 in the set? This 100 is greater than 8, so one value, so we would add a +1 to our answer, and then we would insert this 8 into our set. Okay, so when we insert this 8 to our set would become 8 comma 100. Okay, now we would move next. We would move to 6. We would check how many values are greater than 6 in the set. We can see 8 and 100 both are greater than 6, so we would say we would add +2 to our answer. There are two values which are greater than 6 in our set, and then we would insert this 6 inside our set. Okay, so this 6 has got inserted in our set. Now we would move to the next, which is 9. So we would check how many values are greater than 9 in our set. We can see only 100 is greater than 9. These two are not greater than 9, so they won't be counted. So this 100 is greater than 9, so we would add a +1 to our answer, and then we would insert this 9 in our set. Okay, so this 9 would get inserted. It would become 9 comma 100. Okay, this would be our updated set. Now we would move to the next value, which is 5. Okay, we would check how many values are greater than 5 in our set. So we can see all the 4 values are greater than 5. 6, 8, 900, all 4 are greater than 5. So we would add a +4 to our answer, and we would insert this 5 into our set. Okay, so our set becomes 5 comma 6. Okay, this is our updated set after inserting this 5. Now we would move next to our last value, which would be, so the ending point is 10. How many values are greater than 10? This 9 and this 100, this is greater than 10. So there is only one value which is greater than 10. We would add a +1 to our answer. We would insert this 10 in our set, so our set becomes 10 comma 100. Now once we move ahead, we are out of our basically array. So we have iterated through the whole this vector of pair, and we have added these values to our answer. Our set is updated, so our final answer is just the sum of this, which is 1 + 2 3 1 4 8 and 1 9. So and final answer is going to be 9. We can see for the second test case our answer was 9. Okay, so this was a quick dry run of what we are doing. Okay, so now I hope you understood. We just sorted them based on starting points. So whenever we are moving down, whichever value we are at, all those things that we have inserted in the set, they had starting points before it. So we only need to check the values who have ending point after 9. So we just calculate the count of the values which are greater than this the current value in the set, add that to our answer. That way we would just move through the whole array, and then we can compute our final answer, which would give me the basically the number of pairs that are like this. Okay, I hope you understood the approach and the dry run, so we can move to our code to look how we are going to implement this. Okay, so you can see the code. Okay, int denotes that it would store integers. Less int denotes the comparison. It means it would store the values in ascending order. If you want to store them in descending order, you would write greater int here. Okay, and rest of the things you can just ignore and copy paste. That's not required. So this whole thing you need to write. So instead of writing this again and again, we define them using hashtag define as oset. Now in order to declare our set, we would just write this oset, which basically means this whole thing, and then st. Okay, so inside our code we would just copy paste this hashtag define. These 4 lines we would copy paste, and in order to use, we would write oset st, and we would declare a set, an empty set, an empty ordered set would be declared just by writing this line. Okay, I hope you have understood how to use an ordered set. Now let's look at the full code. We took the t test cases, and inside t test cases we took all the input n, and in a pair I am storing all the starting and ending points. We have n starting and ending points that I am storing in a vector of pair. So vec I dot first and vec I dot second. Dot first represents ai, dot second represents bi. Now I have sorted this vector. So when sorting a vector of pair, it would be sorted based on dot first. Okay, if we are not defining any external comparator. So that only we need to do. We need to sort based on the starting point. So this is sorted. Then we declare an ordered set which is initially empty. Okay, and we declare our answer variable equal to 0. So in this we would add to our answer for every iteration the plus whatever we need to do. Now we would move from I equal to 0 to n. So we would basically move in this vector which is sorted. So while moving, what we were doing here, whenever we move to an index, we just find out for the ending point how many values in the set are greater than this. So how can you find that? So vec I dot second is our x. We need to find how many values are greater than vec I dot second. So we would write st dot order of key vec I dot second. This would return how many values are less than this. Okay, this would return how many values are less than this. If we I is what is I? If we are inserting in the set one by one, when we are at the ith index in zero based indexing, we have already inserted I elements in our set. So this is basically the size of the set. You can also write it as st dot size. There is no problem. The size of the set would be I, because for every iteration we are only inserting in the set one time. So I minus number of values that are greater, number of values that are smaller. This whole thing would give me the number of values, how many values are greater than x, where x is this thing. Okay, so that we are adding to our answer plus equal to. Okay, now we are inserting this ending point into our set. Okay, these are the two things we are doing in every iteration. After the loop in the answer variable, we would get our final answer. We are printing that up. I hope you understood the code. If you look at the time complexity of this code, now this input part is taking basically O of n time, n inputs are there. Now this sorting would take an order of n log n time. Okay, and this inside this, this order of key function takes a log n time. So this is working in log n time. This insertion also takes a log n time. So this is total log n time which is done n times. So overall it's taking a complexity of n log n. Okay, so n log n here and n log n here. The maximum complexity in this code is n log n. So we can write the time complexity for our code is order of n log n, which is well accepted for n equal to 2 into 10 to the power 5, the constraint that we are given. Okay, and if you look at the space complexity, then what all things, we are using a vector of size n. We are sorting this again in this set. At max we would have n insertions, so this is also order of n. So our space complexity would be order of n. We are using a set of size n and a vector of size n. So order of n space complexity and time complexity. I hope that is clear to you, and this problem is very clear. Like this problem in overall was a very good implementation of the ordered set, which is very useful thing. You should learn more about it if you wish. And other than that, like if you don't know about ordered set, then there were also other ways to solve this problem using something like a segment tree or a Fenwick tree. You can maybe try to think how you can solve using that, a segment tree or a Fenwick tree, but this was the most easiest way to solve this problem. That's why we solved it using this approach here. But if you don't know about ordered set, let's say, and this problem is coming in a contest and you know about Fenwick tree or segment tree, then you can also solve this problem using that. Okay, so I hope this is clear to you and you like the explanation. Thank you very much for joining in.